Suppose you're given a training data of 500 emails. Out of those 500 emails, 100 are spam and 400 are not spam. Of the 100 that are spam, the word discount, it appears in 80 of them, and the word free appears in 70 of them. On the other hand, the 400 emails that are not spam, the word discount, it appears in 20 of them, and then the word free appears in 40 of them. This is the tabular representation of this. Now you're given an email and it contains the word discount and free. Then what is the chance, what is the probability that this given email is spam? In other words, you have to calculate probability of spam given that the word discount and free is present in that. These types of questions would be answered through naive Bayes. So naive Bayes, it falls under supervised machine learning. It is used for classification tasks, not for regression tasks. If you recall, regression tasks are the one where you're trying to predict a numerical value. So in this case, we are not predicting a numerical value. We are predicting what category a data falls under. So it falls under classification task. Now, in order to understand naive Bayes, you have to understand the Bayes theorem first. So this is the mathematical formulation of a Bayes theorem. Here, from a machine learning perspective, your Y, it refers to your class label. For example, whether an email is a spam or not. That's what your Y represents. It's an event. X, on the other hand, it represents feature vector. For example, the words in your email. So, for example, let's say these are your email data right here. And these X1, X2, X3, these are your columns. So in this case, this is my X right here. And this would be my Y. This is a label. This will tell you whether email is a spam or not a spam. In this case, your X1 could be maybe it could mean that the word discount is present or not present. X2 could be mean maybe it could be a column representing the word free. Maybe the word free is present or not, or maybe how many times it's present. So this type of data. This one, probability of Y given that X, this represents probability of a class Y given the feature X. Then probability of X given Y, that would be this. This represents probability of observing those features given Y. Y again refers to your class label. And probability of Y refers to your probability of the class Y. And probability of Px represents the probability of the feature X right over here. So in this case, the class that is given a highest probability, your classifier is going to predict that class. So for example, in this particular instance, let's say you have two class, spam and not spam. And let's say your spam is zero point 0.2. The probability that it is a spam is 0.2, which is right here. And the probability that it is not a spam, let's say it is 0.8. And let's say the label for this is 0 and the label for this is 1. So in this case, your classifier is going to predict a class 1. In other words, not spam, because this number is higher. By the way, this argmax is basically means is going to get you the argument or the index of the element that has the maximum value. So the index of this is 0 and the index of this is 1. So it's going to return 1, and this is how you get 1. Now, why do we use the word naive in the naive Bayes classifier? Well, that's because it makes a big assumption, an unrealistic assumption. And that unrealistic assumption is this, that all features are independent of each other in a given class. So let's understand this through an example. So in the case of spam classification, we assume that the words discount and free are independent of each other. So if let's say this is my X1, this X1 represents the word discount, and X2, let's say, represents the word free. So in naive Bayes, we are making an assumption that your X1 and X2, your free and discount, are completely unrelated with each other. They are completely uncorrelated. In other words, the absence or presence of the word discount has no effect, okay, has no effect in the presence and absence of the word free. That's what it means. And so this makes your math a little bit easier. So in this case, by making this assumption, I can rewrite this expression, probability of X1 comma X2, given that your Y is your basically label, which is an email, is a spam or not a spam. In this case, basically this means the probability that the word discount is present and your free is present, given that email is a spam or not a spam, is equal to the probability of your x1, given that y, multiply by probability of x2 given y. And we can rewrite this expression like this because we are making that naive assumption. So this is the general form of this expression. So naive Bayes, by the way, it works extremely well in many applications, especially when you're dealing with text classification. Just on a side note, this assumption is almost never true in real life. You will always find that your features are usually correlated. Maybe there might be some less correlation, but you'll always find some type of correlation between the features. But by making this assumption, it makes the math easy. And now the final Bayes formula. So the probability of y given the feature x1, x2, xn, these are my features right here, okay, and y is the label. The probability of that y of that label given that x1, x2, xn is equal to this expression. This is your Bayes theorem right here. And then we apply our naive assumption. And using our naive assumption, which is this right here, I just showed you this expression. Using this assumption, this right here, this term, it expands into this term. All right. And then if you look at your denominator, each one of the denominator for each one of these classes is always going to be constant. So I can rewrite this expression right here. I can say that this line or this particular property of y given that x1, x2, xn is proportional to the numerator. And your numerator is probability of x1 given that y times probability of x2 given that y, and you keep going all the way to the last feature times probability of your y. So I'm just removing the denominator and I'm just saying that this is proportional to the numerator. Now let's understand all this through an example. So suppose you're given a training data of 500 emails. 100 of them are spam and 400 are not spam. The question is this: what is the probability that a given random email is a spam? In other words, compute your probability of spam. But in this case, my spam, the total number of spam is 100. So my probability of spam would be 100 divided by the total number of email, which is 500. And the answer comes out to be 20%. So it's 20% chance that a given random email is a spam. Now I give you some additional information about this training data. The 100 emails that are spam, the word discount appears in 80 of them, and the word free appears in 70 of them. In the 400 emails that are not spam, the word discount appears in 20 of them, and the word free appears in 40 of them. So this information is represented right here in a tabular format. Now your question is this: what is the probability that a given email is spam given that it contains the word discount and free? In other words, you have to compute probability of spam given that discount and free is present in it. So here we have to calculate this right here, probability of y given that x1, x2. Your y in this case represents the spam, and your x1 and x2 represents that your this is a discount and your x2 is free. So this would be represented by this expression right here. This is your Bayes theorem. Now we are assuming that your x1 and x2 are independent. In other words, your discount and free are completely uncorrelated with each other. By making that assumption, I can rewrite this expression as probability of x1 comma x2 given that y is equal to this multiply by this term right here. Now substitute these two terms right here in this expression. So the probability of y given that x1, x2 will turn into this expression. Now your denominator is going to be constant for both your y, when your y is a spam or not a spam. So in this case, I can ignore my denominator and I can just rewrite this expression as proportional. So I can say probability of y given that x1, x2 is proportional to probability of x1 given y times probability of x2 given y times probability of y. Now we calculate each one of these terms, this term, this term, this term separately. A little terminology alert. This expression is referred to as posterior, this referred to as likelihood, and this is called prior. And the reason this is called prior is because this is the probability of obtaining y before you observed x1 and x2. And this is called posterior because this is the probability of y after you have seen the evidence of x1 and x2. Step 1, compute the priors. So first compute the probability of a spam. In other words, compute your probability of y. And probability of a spam would be the number of spam emails, which is 100, divided by the total number of emails, which is 500. And the answer comes out to be 0.2. In other words, 20% chance. And likewise, compute your probability of not a spam. So probability of not a spam, this would be equal to the total number of not spam emails, which is 400, divided by the total count, which is 500. The answer is 80%. So in this case, it is 80% chance that your email is not a spam. Step 2, compute your likelihood. So probability of discount given that spam. In other words, you have to calculate probability of your X1 given that your Y is spam. This will be equal to, you count how many discount word do you see in a spam email. Well, that's given to you as 80 right here. Okay, so it's 80 divided by the total number of emails that are spam. And how many emails you have? 100. It's given to you right there. So the answer is 0.8, 80%. Well, now you calculate probability of free given that email is a spam. In other words, probability of your X2 given that your Y is spam. That will be equal to the total number of the times the word free appears in your spam. In this case, it's 70 right here. And the total number of emails which are spam is 100. So 70 divided by 100 and the answer is 0.7. Likewise, compute your probability of discount not spam. In other words, compute your probability of X1 given that your Y is not a spam. In this case, your how many times the word discount appears in email that is not a spam. Well, in this case, the answer is 20. So it's going to be 20 divided by 400. 400 is your total number of emails that are not spam, and the answer is 0.05. Likewise, probability of your X2, given that your Y is not a spam, would be equal to, you just count how many times the word free appears in email that are not spam. Well, the answer is 40. So it's going to be 40 divided by the total number of emails that are not spam. And the answer is 0.1. So I'm able to calculate this right here. I know this and I know this. And now the posterior. So for each class, calculate the probability of spam given that the email contains the word discount and free in it. In other words, you have to calculate the probability of Y given that X1, comma, X2. And we know that from this expression right here, that that would be proportional to probability of your X1 given that it is Y multiply by probability of your X2 given Y times probability of your Y. And this is exactly what that expression is right here. Okay, substituting your values in there. These values I got it from previous step. All these values from here. Substituting your value, the answer is 0.112. So probability of spam, given that it's a discount, given that it contains the word discount and free, is proportional to this number right here. Likewise, probability of not a spam, given that the email contains the word discount and free, is proportional to, using the same expression as above, right here, the answer comes out to be 0.004. So this number right here, 0.112, is a lot bigger than 0.004. Therefore, the email that contains the word discount and free is a spam. It falls in this category. It's a spam. Now, the above values are not normalized. They are not truly your probability. So we're going to normalize that. And the way you normalize them is you divide by the total sum. So in this case, you divide by 0.112 plus 0.004, and this will give you the probability of a spam given that the email has the word discount and free in it is 0.97. Likewise, the probability that email is not a spam given that it contains the word discount and free is 0.03. Conclusion, if an email contains the word discount and free, then it is a 97% chance right here that it is a spam. So there are different types of Bayes classifier based on the data type they handle. The first one is Bernoulli naive Bayes. This one is designed for features that are binary or Boolean in nature. It is effective in scenario where data is represented, for example, like yes or no, true or false, or 0 and 1. So an example would be spam detection, sentiment analysis. And then you have multinomial naive Bayes. This one is ideally suited for discrete data. This is pretty good at handling features that represents counts. For example, your word frequency in documents. And it is very commonly used in your text classification for your text classification and also for document categorization. And then you have Gaussian naive Bayes. So this is suited for continuous data. For example, in the case of numerical data, so for example, such as measurement or sensor readings. So a question, which naive Bayes classifier should you use if you have mixed data type in a feature space X? Well, the answer is this. First, you do label encoding and then you use Gaussian naive Bayes. So suppose these are your features X1, X2, X3, age, income, gender, and department. In this case, you can see that this is continuous, continuous. This is your categorical right here, categorical. So in this case, first you do is label encoding for each one of these values. So in this case, your gender gets label encoded and your department gets label encoded. And after that, you employ Gaussian naive Bayes. Now, let's look at some of the advantages of naive Bayes. The first one is that it is very simple and easy to implement. Well, that's because it's based on simple basic probability rules. It's easy to understand and easy to code. You don't have to do any scaling or standardization. Also, it requires a very little parameter tuning. Second, it works extremely well for large data set. Here, your training is fast because it only calculates probabilities. It works efficiently even when you have a millions of records, a large number of records. And this makes it a perfectly ideal for real-time predictions where you need predictions really quick. And the third, it performs pretty well in a high dimensional data. So it works well when you have a large number of features. For example, in your text, you have a large number of words over there, spam detection, document categorization. In these types of scenarios, the number of dimension is very large because you have large number of words. So it works pretty well in these types of cases. And now let's look at some of the disadvantages. First of all, is that it makes an assumption, the naive assumption that all features are independent. Well, in real world, your features are usually correlated. For example, hot and sunny in weather condition. The presence of the word hot and sunny, they are correlated. And this way, since you're making that assumption, it can reduce your accuracy.